Hello, everybody. I'm Félix Neutatz, and today I'm happy to share our ideas on data cleaning and data engineering from machine learning. So let me introduce myself. I'm a PhD student at the Databases and Information System Group at Leibniz University in Hanover. And I'm also a researcher at the Berlin Institute for the Foundations of Learning and Data, in short, BIFOLD. The work that I present today is joint work with Binga Chen, Professor Siavash Abedian, and Professor Eugene Wu. If we are interested in data cleaning for machine learning applications, we first have to understand the environment of these ML applications. And so for that, to understand, I have here a workflow of a company who wants to predict promotional discounts, like whether to give promotional discounts to a customer or not. And this workflow is divided into 3 stages and 3 teams. So first we have the data management team that is responsible for ingest and validation. So they will ingest user profiles from external sources and purchasing and browsing history from internal sources and validate this data. Then they will forward it to the data science teams, which will, on the one hand, predict the churn. That means the likelihood whether some users will leave the platform. And on the other hand, they will model another machine learning model that predicts the preferences to different products. And then these estimations will be handed off to the marketing team in blue, which will then decide, based on this information, whether to award this promotional discount to a user or not. And on the side, they will also monitor the churn, so whether people are joining or leaving this platform. So in total, you can see this is a quite complex workflow, and it's not trivial to know at what stages we actually should do the cleaning. And if we look at the very beginning of this workflow, we have the data. And now the question is, how does this kind of data look in the real world in these ML applications? And I have here an example for such data, and it can be quite messy. For example, here we have uniqueness violations, we have wrong representations, so the name is in the wrong order here, or sometimes people might put the wrong information into the wrong field. So for example, here a name was inputted into the birthday field, or we can have contradictions of values. For example, if you're born on the 19th of September, 91, then you're not 27, but slightly older. You might have missing values, formatting issues, incorrect values, or just simply typos. And of course, in the setting of machine learning, we might also have incorrect labels. So to conclude here, real-world data can be quite messy, and everybody knows that if you put garbage into an algorithm, you also get garbage out. And this is, of course, economically wise, a really big problem, because we lose a lot of money when we have messy data. So now you might say, well, that's not a problem. We have in the data management community a lot of data cleaning systems, for example, Raha and Baran, which are cleaning systems coming from our lab, or HoloClean, Nadiv, OpenRefine, or many other solutions from industry that you can just apply on dirty data, and then you get the clean data out, and then you can just apply your machine learning model. But it's not always that trivial, and I will come to that why in a moment. So I will describe the problem here with a data set. First, we have the flights data set, where we want to predict whether certain flights are delayed or not. And we split the data into a training and to a test set. And both of these sets we have in 2 versions. One is clean and one is dirty. And as expected for this data set, we can see here that we get the best accuracy when we use both sets in the clean state. And we get the worst accuracy if both sets are in the dirty state. So this is just as expected. But we also analyzed a second data set, namely the US Census data, where we want to predict whether a person earns more than $50,000 a year. And here, surprisingly, we see that if we use both training and test in the dirty version, we actually get the best model accuracy. So just imagine you put all that effort on cleaning both the training and the test, and you actually get a worse accuracy than if you would have just used the dirty version. So this is surprising. And the other interesting thing we see here is that if we would have just cleaned the training data, but not the test data, we get really, really poor performance here. So the reason is that the distributions between clean data and the distribution of dirty data is really significantly different. And so it breaks the assumptions of machine learning that both distributions come from similar distribution. So to conclude, cleaning interventions are dependent on the type of error, but also on the application. But this is not the only challenge that we have in cleaning for ML. We have many more. So for example, as I showed in the beginning, cleaning is fragmented across different roles and different parts of the workflow. So local cleaning decision can have really global impact and a negative one. And also, if we compare the data to the data that we have commonly in the data management community, data for machine learning is much more complex and dynamic. So we have multi-model or unstructured data. So we have images, videos, sound, text. On the other hand, we have population level errors. So even if specific records are clean, but if we have unrepresentative sample of the data, this might lead to bias in the later model stages. So this is also different to what we have in the data management community. Furthermore, of course, cleaning has to generalize to unseen test data, and also the data shifts over time. And to address these challenges, I want to take you on a journey to an end-to-end application-driven approach toward cleaning. So we will start off by explaining cleaning before ML. So that consists of traditional cleaning and ML accelerated cleaning. And then I will continue with cleaning for ML systems, and finally finish with our proposal for holistic cleaning framework. So let's dive right in. So traditional cleaning systems are, for example, pattern and rule-based cleaning systems. So for example, you can use regular expressions or functional dependencies. So just like in a sieve, the data runs through that sieve, and the good data would go through, whereas the remaining data should be corrected and cleaned. Then we have outlier-based cleaning, where everything that is too far away from our distribution should be cleaned. And finally, we have external data-based cleaning, where we can use, for example, a knowledge base to do a dictionary lookup and replace the dirty version with the one that is in the knowledge base. The disadvantages of these approaches is that if you really want to cover a large number of error types, we have to run multiple of these cleaning systems, and that's obviously a large effort to do so. And therefore, ML-based or ML accelerated cleaning approaches have been proposed. So the main idea here is that we formulate cleaning as a machine learning task. So more specifically, we formulate a classification problem, such as, is a value erroneous, or which is the correct value for a given erroneous value. But this approach has two problems. On the one hand, this labeling can be quite subjective. So if you look here at a dish of snails, there are some people who might say, this is an amazing dish, you should definitely try. And other people might say, this is an error. So this is a big problem. So you have to find consistent ways of labeling these errors. And the second problem is, of course, that you need not only a few of these labels, you need quite a lot of them for machine learning to learn these patterns for these errors. And in order to reduce this user effort, there have been some approaches been proposed that, for example, use label propagation, active learning, data augmentation, transfer learning, or self-supervision. But still, similar to traditional approaches, ML accelerated cleaning still cleans in isolation from the application. So we do not consider the application in this cleaning step. And in order to do just that, cleaning for ML systems have been proposed. So what is the main idea here? So we just want to clean those parts in the data that actually affect our application negatively. So cleaning for ML systems leverage the downstream model or application to guide cleaning. And we proposed a categorization scheme for these cleaning for ML systems, which contains 4 questions. So first, how does the system repair the data? Second, does the system require access to the entire source of the machine learning application? And which signal of the ML application is used to guide cleaning? And finally, which ML models are supported? To describe this scheme a bit more in detail, I have an example here. So there's, for example, Activeclean is a well-known cleaning for ML system, and it is proposed by Krishnan and all. And it aims at cleaning training data. So first we have the training data. We train some machine learning pipeline with a convex model using stochastic gradient descent. And the system will choose based on these gradients which of the records have the highest impact or are most likely to be erroneous, and forward these records to a user or human operator who will then in turn correct these records, and they will replace the original records. And in an iterative process, we converge more and more towards clean training data, and it also has some nice conversion guarantees. The problem with this approach is unfortunately that it only cleans the training data and it requires a convex model. So if we have dirty test data, this approach might not work. So therefore, there's also another approach, which I call the AutoML approach. So we have our data and we split it into a training set and a validation set. And we assume here that the labels for this validation set are correct. And we can use the validation score to choose only those cleaning preprocessors that actually maximize our validation score. And this is a nice approach, and we are currently working in our lab to work more in this direction and try out different cleaning preprocessors to follow this AutoML approach. But yet still the disadvantage here is that all the proposed cleaning for ML systems still cover only specific aspects of cleaning or specific error types, dataset components, or ML models. So in order to avoid that, we have to follow a holistic approach. And this is exactly what we propose in our vision. We want an end-to-end application-driven approach toward cleaning. So remember, we had our use case of a company that wants to decide how to whether to give a promotional discount to the end user or not. And the main idea of our vision is that we collect all the possible signals from this workflow, starting with the data management team. They might specify some rules or regular expressions or patterns, which we will send to the signal collector. Then in the data science team, we might get, for example, gradients or validation scores. And even the end user might send a signal saying, maybe I should have gotten this promotional discount, but I did not, so something clearly went wrong here. And we collect the entire signals of this entire workflow and forward them to the cleaning optimizer. And then the cleaning optimizer has access to a cleaning library, which contains all the systems that I just explained, like traditional cleaning system, ML accelerated cleaning systems, and cleaning from ML systems. And based on the signal it gets, it decides where in the workflow and on what parts of the data it should use which systems. And on top of that, of course, we also have provenance. So if the optimizer makes a wrong decisions, or maybe we get some new signals that say that point at the direction that maybe we should follow a different cleaning strategy, we can use this provenance to roll back our decisions and maybe replace a cleaning system with another one. And finally, the instrumenter will put all these cleaning systems into the right place in the workflow in order to make this really work. And of course, at the moment, this is the early days. At the moment, this is just a vision. But in our lab, we work really hard to make this vision reality. But there are even some challenges that go beyond this vision. And these I want to talk about here real quick. So there is the clever Hans phenomenon, also known as spurious correlations. So what does it exactly mean? So on the right side here, we see a picture that contains a horse. And a neural network might correctly identify this picture containing a horse, but maybe only because we have a text here that says that this picture is coming from a website that has horse pictures. So if we would give the neural network another picture of a horse without this text, it might not be able to predict this, to predict it correctly. And therefore, removing these spurious correlations, so in this case, the text, is quite challenging. So this is a really interesting challenge. Another challenge is model entanglement. So nowadays, models act more and more as data sources for other models. So if we update single models somewhere upstream, this might completely degrade the end-to-end performance. So we have to work on versioning systems and also verification systems in order to avoid these kind of problems. Furthermore, as I said before, there's the population level errors. So if we do not have a representative sample, so if we have biased sampling or systematic data generation errors, this might also cause bias in the data and therefore also leads to bias later on in the machine learning models. So addressing these kind of population level errors is also quite challenging. Furthermore, we have violations against social and cultural norms. So it's already extremely hard to detect things like hate speech, misinformation, or privacy violations. But what makes it even harder is that these kinds of norms also change over time. And finally, we have robustness. So some adversaries might introduce erroneous values on purpose to trick the system into misprediction. And of course, we have also a large community who is working just on this problem. So to conclude, what should you take home? First of all, that naive cleaning before ML might actually degrade performance, and that you should consider cleaning in a holistic view and incorporate all possible cleaning systems and signals in an end-to-end application-driven approach towards cleaning. And if you have now more questions, or if you have interesting use cases or data sets, we would be really curious, and it would be great if you can send us an email. And with that, I'd like to thank you and goodbye.